In Chapter 27, we showed that light behaves like a wave and demonstrates the effects of interference and diffraction. This helped to verify Huygens' wave theory of light, which would eventually be described mathematically by Maxwell's theory of electromagnetic waves. Until the wave properties of light were demonstrated, the prevailing viewpoint on the nature of light, supported by Newton and others, was that light was composed of tiny classical particles. This description of light was known as corpuscular theory. However, we will see that later experiments involving light could not be explained by a wave theory, but could only be understood using the particle picture of light. Eventually, it would be accepted that in certain situations, light would behave like a wave, and in others, it would behave like a particle. This became known as the wave-particle duality of light. One question that may be obvious to ask is, if light, a wave, can behave like a particle, then can a particle, a very small piece of matter, behave like a wave? As we will see in this chapter, the answer to this question is an extraordinary yes. As an example, consider repeating Young's double slit experiment, but instead of shining light on the two slits, shoot a beam of electrons at them. An electron is a particle, a tiny bit of matter. We would expect the electrons that pass through one of the two slits to travel straight through and impact the screen directly behind the slit. If we assume the screen lights up wherever the electron strikes it, we should see just two bright fringes, one directly behind each slit, as the figure shows. However, what we actually see is an interference pattern, exactly as if we had performed the experiment with light. The conclusion is inescapable. The electrons in a double slit experiment act like waves and interfere when they pass through the double slit, and then impact the screen like a particle. At the subatomic level, even matter obeys a wave-particle duality, which is stated as follows. Waves can exhibit particle-like characteristics, and particles can exhibit wave-like characteristics. Experiments through the first half of the 20th century demonstrated the particle characteristics of light and the wave characteristics of matter. These laid the foundation for changes to our fundamental understanding of the universe and its description by classical physics. In fact, a new branch of physics, known as quantum mechanics, will have to be developed to correctly understand the subatomic world. We will see that quantum theory allows for some very strange phenomena, oftentimes at odds with our common sense.